Good day, everyone. In this video, we are going to talk about the different shift key-in or modulation techniques and describe their advantages and the disadvantages and the uses. Okay. All right. And then to transmit digital data with discrete analog signals, there are three basic techniques you can consider: the amplitude shift key-in, the frequency shift key-in, the phase shift key-in, and one can then even combine two or more of these basic techniques to form more complex modulation techniques such as quadrature amplitude modulation. Okay, let's take a look at the first one. So again, to transmit digital data with discrete analog signals. So we are going to look into the amplitude shift key-in. Before we give you the explanation, the word discrete over here means that it has a finite set of values. So if we look at the signals over here, you can see that it has two different amplitude. Amplitude means the height of the wave over here. So this one is about pretty low, but then this one is higher one. Okay, and then you can see the frequencies about the same. Okay, so that's why it's called a discrete analog signal. Okay, and then with that understanding, then we can say that we can use one amplitude to represent a value of 0, digital value of 0, and while another amplitude to represent the digital value of 1. Okay, so you can see that we can use this low, again low height of the wave to represent the digital value of 1, and then this one higher one represent the value of 0. So we can again transmit data. Depends on digital data. Depends on what kind of the amplitude we want to use, but we use only two of them here. Okay, so figure 2-15 shows an example of amplitude shifting key. Okay, shifting key. So this one use 4 different kind of amplitudes. So you can see that this one has a lower, very low height on the waveform over here, and then a little bit higher, right? A little bit higher, right? And then this one again higher than the previous two. Okay, and then this one is the highest one. Okay, than the previous 3. Okay, so we can again use different amplitude. Okay, this one to represent digital data of 0, 0. This one 0, 1. Okay, this one 1, 0. Okay, this one 1, 1. Okay, so figure 2-16 shows an amplitude shift key-in using 4 different amplitude labels. Okay, and then over here, I put a note that here we have 4 different amplitudes. Amplitudes. So we can encode 2 bits in each signal change. Okay, and then the number of bits per signal change. You can use the formula over here. Just take the log base 2 followed by the amplitude levels. So in this case, we have 4, right? Different kinds. That means that the number of bits per signal change. That means 2 bits. Okay, Okay, next one, we're going to talk about the frequency shift key-in. So again, you can see that frequency means that within certain time interval. I mean the how many cycles this waveform can complete. You can think of this one as within the same time interval. This one, the cycles will be maybe about 1.5 cycles, right? Okay, waveform. Okay, so this is one cycle. Okay, or maybe 1.5 would be fine. But then this one has more, right? Okay, kind of 1, 2, 3. Okay, kind of 3.5. Okay, if you want to think about it. So it kind of we use two different kind of frequencies, okay, but then same amplitude, okay, which means same height, okay, for the signal wave, okay, yeah. So frequency shifting key use two different frequency ranges to represent data values of 1, 0, and 1, as shown in the figure over here, okay, yeah. So again, then we can use this frequency to represent the digital value of 1, this one to represent digital value of 0, and then 1 and 0, okay, yeah. All right, okay, and then we can also use another technique called a phase shifting key. Okay, so again, this one you can see that they all have the same amplitude, and then almost the same frequency as well. Yeah, but then we can take a look of the so-called, we can use the so-called phase change. Okay, phase change means that, for example, you start from here, go up, right, go down, go up, go down, go up. Okay, so at this point of time, theoretically, it should go up, right? But then we decide to change direction of the waveform over here. We say, hey, I mean, go down, okay, go down, okay, start go down, okay, instead of going up, right? So it creates so-called, okay, at this moment of time, it creates so-called phase change. Okay, so hey, go down, okay, start go down, going down, up, down, okay, up, down, okay, and then at this moment of time, okay, and then it will go down, okay, yeah, so going down as well. So we say that, hey, I mean, no phase change, yeah, so okay, over here, okay, go up and go up and go down and go up. Theoretically, okay, at this moment of time, it should start going up, right? But then we say, no, okay, I want to change the direction, okay, so it goes down, so it creates a phase change, okay? And then again, we can use this technique again to say that, hey, if there is a phase change, one phase change, we can encode a value, while another phase change, we can encode the value of 1, okay, yeah. So, if this one, we use this one, as value to represent digital value of 0, okay, then when there's a phase change, we say, hey, I mean, this signal represent a 1, okay, yeah, and then again, low phase change means going down, right? Still going down and up. Then it's a 0, and then over here a phase change, then it means that the next analog wave represent the value of 1. Okay, yeah. So yeah, figure 2-18 shows an example of a simple phase shift key in of a sine wave. Yeah. And then based on this phase shifting key in technique, actually you can apply this some kind of direction change at the different angles, 45 degrees, 135 degrees, 225 degrees, 315 degrees. So we call those as quadrature phase shifting phase shift keying. Okay, yeah. So here will be a figure 2-19 shows 4 phase angles of 45, 135, 225, and 315 degrees, as seen in quadrature phase shift keying. Okay, so here you can see the Okay, it's going up, going down, going up, going, okay, yeah, going up. Theoretically, you should go down, but then starting from here. But no. Okay, over here, okay, say, hey, we want to do a 40-degree, phase change. Okay, so so you can see that instead of starting from here, going down, it kind of shift a little bit, right? Okay, so it becomes start from here. And then we can use this one to send the digital values of 1, 1. Okay, and then here is another example. It should start going down from here, right? But instead, we kind of move this one to the left. Okay, so it has a phase shift key of 135 degrees, and we use this one. Okay, yeah, we use this one to represent the value of 1, 0. Okay, and then this one again has a phase shift angle of 225. Okay, so we use this situation to represent the value of boundary value of 0, 1. And then this one has the phase shift angle of 315. Okay, then we can use this situation to represent the boundary value of 0, 0. Okay, yeah. All right. Okay. So next one, you mentioned about the quadrature, amplitude modulation. Okay. As an example of QAM, 12 different phases are combined with 2 different amplitudes. Okay, so you can see that here the amplitude, which means the height of the waveform, above, below the reference line are almost now, are the same. Okay, yeah, but then we can also use different height of the waveform. Okay, so that is what this slides try to say over here. Okay, with 2 different amplitudes. Okay, so since only 4 phase angles have 2 different amplitudes, there are a total of 16 combinations. And then with 16 signal combinations, each baud equals 4 bits of information. So which means that with this kind of 16 combinations, then we can represent 4 bits, 4 bits of data. Okay, yeah. So here will be the picture, figure 2-20. Shows figure A, shows 12 different phases. Yeah. So again, this 190-degree section. We separate them into 4 different angles, right? And then we can see that we have let me see. Yeah. We have kind of let me see, 16 different combinations. Okay, yeah. So 1, 2, 3. 1, 2, 3. Yeah. And then sorry, I will say 12. Okay, 12 different phase change. And then Y figure B. Okay, this figure B. It shows a phase change with 2 amplitudes. So you can see that here has a higher or taller amplitude waveform, but then this will be a lower. Okay, this will be lower. Okay, so figure here B shows 45-degree phase change with a high amplitude. Okay, a high amplitude, but you can also have a 45-degree phase change. But then with a low amplitude. Okay, yeah. So again, the purpose is to allow us to carry more data bits. Okay, yeah, more data bits in the signal. Okay, yeah. So I will stop the video here. Okay, yeah.